we have a fourth degree polynomial equation, and to solve it, we're going to set it equal to 0 and factor. Remember that in a polynomial, we can expect to have the same number of solutions as the degree. And all of those solutions should work because polynomials do not generate extraneous solutions. So we begin by setting this equal to 0. We'll subtract 81x from both sides. To get 3x to the fourth minus 81x is equal to 0. Then we'll notice that we have some common factors. There's a 3 and an x that's common to both of these terms. So we factor out the 3x, which leaves x cubed from this term minus 27 from this second term. And we're still equal to 0. Let's recall the difference of cubes factorization. If we have two quantities being subtracted where each has a cubed root, this can be factored into the cubed root of the first. This first sign is the same as the original, so we'll be subtracting the cubed root of the second. And then we're going to multiply this by a trinomial, which is this first quantity squared. And now we're going to have the opposite of the original sign. Then we multiply these two quantities together. The second sign is always positive. And then we square this second term to get y squared and close up the parentheses. And the acronym that helps us remember the signs in this difference of cubes factorization is S for the same sign as the original. Then we have O for the opposite sign of the original. And this last sign is always positive. And this acronym spells SOAP, same, opposite, always positive. So we have the difference between two things that have a cubed root here, and so the second factor will factor according to the difference of cubes. So we'll copy paste our first factor of 3x, and x cubed minus 27 is going to factor into a binomial times a trinomial, and then all of this is still going to be equal to 0. So to get this first binomial, we start with the cubed root of the first term, which is going to be x, with the same sign that we started with, so that's minus, and then the cubed root of the second term, which is 3. And then the trinomial is going to be this quantity squared, which is x squared, with the opposite sign of the original, which is plus. We then multiply these two quantities together to get 3x. This sign is always positive, and finally we square this last term to get 9. Now let's take a close look at this quadratic and notice that it's prime, meaning that it doesn't factor any farther over the real numbers, because there are not two factors of 9 that add to 3, so we would consider this then to be completely factored. Once the polynomial is completely factored, this is when we set each factor equal to 0. So we have 3x set equal to 0, x minus 3 gets set to 0, and this irreducible quadratic also gets set to 0. Now we want to solve each of them individually. We'll divide both sides by 3 here. Canceling the 3's on the left, we get that x is equal to 0. We add 3 to both sides here, which yields x is equal to 3. And then to solve this quadratic, we already know that it doesn't factor, so let's use the quadratic formula to solve it. Recall that the quadratic formula is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So for this quadratic, we have x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c, and we have our b plugged in here. A is 1, c is 9. And then all of this is divided by 2 times a, and our a coefficient is positive 1. And so now we just need to simplify this quantity. So we have x is equal to the opposite of 3 plus or minus the square root. We have 9 minus 36 under the radical, which is then all over 2, which becomes negative 3 plus or minus the square root of negative 27 all over 2. Let's notice that the square root of negative 27 can be written as the square root of negative 1 times 9 times 3. Negative 1 has a square root that is I. Positive 9 has a square root that is 3, and this 3 needs to stay under the radical, so we just leave it as rad 3. So let's replace the square root of negative 27 with 3 times I times the radical 3, and then we're written all over 2. So let's bring all our answers together. We have x is equal to 0, x is equal to 3, and x is equal to -3 plus or minus 3i rad 3s all over 2. Notice that we actually do have 4 solutions here. Noticing that this is a plus minus, which means this is actually 2 solutions in this region, so a total of 4. And all of these solutions work. Remember, polynomial equations do not generate extraneous solutions. So now let's check our answers on our calculator, and we'll begin by testing the complex solutions. Let's enter this complex number in standard form, so we'll say alpha f1 to get a numerator denominator, and input -3 divided by 2, plus another fraction, so alpha f1, numerator denominator, and then select 3 radical 3's divided by 2 to be the real coefficient of our I, the imaginary number, so we'll hit second I, and then store all of this into x. So now let's take this back to the beginning with our x plugged into the left-hand side of the equation, and we'll compare that to what it yields plugged into the right-hand side of the equation. So plugging in the left-hand side, we have 3x raised to the 4th power. We'll hit enter to see a complex number that comes out of the left, and we want to compare that to the complex number that comes out of the right. So 81x is the right-hand side, and we can see that we do generate the same 2 complex numbers from the left and the right. So our first complex solution does work. Often I'll skip checking the other complex solution, the negative one. If the complex solution with the plus worked here, then likely the one with the minus works as well. You could check both, but I'm going to move on to checking x is equal to 3. So I'll hit 3 store x, and then enter to input that into the x variable, and then I'm going to check that into the left-hand side of the equation, which was 3x to the 4th power, and compare that to what I get from the right-hand side of the equation, which was 81x. Then we hit enter again, and the 2 sides do match. We can see pretty easily that when I store 0 into x, that's going to work. On both the left-hand side and the right-hand side, the output is going to be 0. So we see 81x on the right also equals to 0. So our 4 solutions did actually work. Again, we were expecting 4 solutions to this 4th degree polynomial, none of them being extraneous.